All right, good morning, class. This morning, what we're going to take a look at is buffer systems and what their use or practicality is. So we'll start out here on the left side, defining a buffer system. It says a buffer is a two-component system that prevents major change in pH. So the idea here, and I'll skip to the third bullet point, it says any small amount of strong acid or base that's added to a buffer will be converted to a weaker acid or base, minimizing pH change. So the idea is if you have some sort of system that's constructed of a buffer, and then if we add a strong acid or a strong base, it's not going to overly complicate things. It's not going to create a major change in dynamic or makeup of the system. And so a buffer is a way to buffer, to kind of protect it from a gross amount of change. So what is a buffer made up of? Well, it's going to be made up of a weak acid and conjugate base, or a weak base and its conjugate acid. Okay, so some examples you might see, for example, a weak base like ammonia with ammonia. Okay, you might see it that way, or acetic acid is a weak acid and its conjugate base is acetate. Okay, so those are some examples of weak acids or weak bases and their conjugates that would make up a buffer system. So again, it's a two-component system: weak base and conjugate acid, or weak acid and conjugate base, and that two-component system is going to prevent major change in pH. So on the right is a sample buffer system, and this is where we see in our third bullet point on the left, if we had a small amount of strong acid or base to a buffer, we're going to convert it to the weaker acid or base, which is already present in the buffer system, and so we're not going to change the makeup of the system very much. So on the right, let's say our buffer system is acetic acid and acetate. If we add a strong acid such as HCl, hydrochloric acid, to the buffer system, it's going to react with the conjugate or the weak base here, the acetate. Now the acetate is going to take the hydrogen, right? It's a base, it's going to accept the proton, and it gives us acetic acid, which is a weak acid here. And then chloride is left as the conjugate base from the HCl. So the idea is that we're taking the strong acid, HCl, combining it with a weak base, and as a result, we form the weak acid that's part of the buffer system. Okay, so we take the strong acid and we are converting it to the weak acid. The buffer system is comprised of the weak acid. So if we take a small amount of something very strong, we put it in the buffer system, it gets created into or changed into the weak substance that's in the buffer. That's good. Okay, we want to make sure there's no negative effect by adding something into our buffer system, and so we convert the strong into the weak. In the case with the strong base, we have sodium hydroxide down here. Okay. And if we take the strong base and react it with the weak acid in the buffer system, acetic acid, it's double replacement here. It's a neutralization reaction where we form sodium acetate, the salt, and water. Now keep in mind that sodium acetate, even though I've written it as a salt, it is still acetate, which is part of our buffer system. So what we've effectively done is we've taken the strong base and we have converted it to acetate, which is a weak base. Okay, so doing a strong base to a weak base is part of this So part of your goal come Tuesday is going to be, can you define a buffer system? Like, what is a buffer? Which comes from the first slide. The second part would be, can you provide an example of a buffer system? So come up with a weak acid and its conjugate base, or a weak base and its conjugate acid. There might be a component where I give you a sample system. For example, maybe I give you chloric acid and chlorite. So maybe I give you something like this and say, can you explain how it behaves in the presence of HCl or sodium hydroxide? And so we're showing, well, HCl is going to react with the base. In this case, it's going to go with the chloride. So you have strong acid, weak base. And the result, we end up with chloric acid, which is a weak acid. And then we have Cl minus, which is our conjugate base over there. So notice we are going from a strong acid, and we convert it to a weak acid. That's the purpose of a buffer system. In the case of sodium hydroxide, we're going to take that strong base and react it with the weak acid, which is HClO2. And the result is that we form chlorite, which is our weak base, conjugate base, and then water. Now, there is a sodium over here. Really, it's the chlorite ion with the sodium, but sodium's a spectator, which just means, hey, how's it going? I'm watching. I don't really participate. I have no effect on the outcome. Just hanging out, chilling. Go team. Okay, so that's a spectator ion. That's what sodium is here. So I'll just write this spectator. Okay, so again, we take our strong base, sodium hydroxide, and we convert it into a weak base, therefore minimizing its impact, and it won't affect pH very much. Okay, the last slide that we have for this unit ever, the importance of buffer systems. So where are they useful? We see it in living organisms like blood. Okay, in our bodies, we have buffer systems in place because if you undergo acidosis or alkosis, that would suggest that our blood pH is either too acidic or it's too basic, and that can lead to illness and death. Okay, seawater, for them fishies and the algae and the plant life, they have a certain pH for their ecological balance. And if you affect it in some way, you could kill the sea life and the fishies. That would be sad. No more Nemo. Dory would probably forget. She just keeps swimming. She doesn't know any better. Just keep swimming. Just keep swimming. Follow the seashells. Yeah. Yep. All the rest of you are looking at that last slide. Buffers are also used in food systems. So like if you have something with citric acid and sodium citrate, citric acid is a weak acid, citrate would be the conjugate base. So you might find something that says, hey, it's got citric acid and citrate, it's a buffer. Okay. Phosphoric acid and sodium phosphate. I see phosphoric acid as an ingredient in some of your sodas. Like Coke, I think, has phosphoric acid. I remember when I was in high school and I got braces. How many of you have had braces? So they have to scrub and clean your teeth before they apply the brackets. And I remember them saying that what they were applying was comprised of phosphoric acid, and that was essentially to clean and to etch the teeth so that there would be a good bonding surface for the bracket to adhere. And they were like, yeah, make sure you don't lick your teeth right now. I mean, you got the thing in your mouth like that one game where it's like, right? So I remember phosphoric acid being used in there. Little anxiety producing, like, oh, you got phosphoric acid in your mouth. Don't lick it. All right. So that's about it for buffers. Like we use them, like blood is a big one, obviously, keeping balance there. Seawater, ecological systems, food, etc. Okay. Any questions about buffers? Okay, this video will be available in a moment on the website and the YouTube channel, Google Plus, and Twitter as always. If you enjoyed this video and found it helpful, like the video, leave a comment. If you're not subscribed to the YouTube channel, go ahead, hit subscribe.